I'll just talk about this part maybe one more time. So there are like 5 imaginary words that we might live in. This 5 imaginary words, so this 5 imaginary words, they connect complexity theory to cryptography somehow, and we will see how. So complexity theory wise, we can be in a world where everything is easy. P is equal MP, there's no hard problem. We can be in a second world where there are hard problems, but everything's easy on average. So the way you can think about it is that here's the space of all the problems that I care about. And if I sample one of this problem randomly, it's definitely like with a high probability. It's with a high probability, this is an easy problem. But in this biggest space, there are some dots that they are hard problems. Right? So if we live in that world, the reason it's called heuristic is that heuristic works really well because there are algorithms that, we can run them heuristically, and with a high probability, they work because everything's supposed to work on average. And for instance, this is a really good for machine learning, if you want to think about it. Okay. Then there is a word which is the worst of all, and that's why it's called pestilence, because there is problems are kind of hard, kind of easy, but it's very useless in terms of algorithms, but it's also very useless in terms of cryptography. So in the pestilence, you have hard problems, they exist, but heuristic don't work. Right? It's not like I have this average case easiness either. I don't have a guarantee that on average things are easy. I have some hard problems, but I don't know where in this land they live, right? And so the thing about the first 3 words is that if we live in one of these 3, there is no one-way function. And cryptographers so far, they have established that if there is no one-way function, there is no cryptography. If there is no problem that I can reduce it somehow in a way that something is easy in one way and it's hard in the other way, then there is no way for constructing cryptography. So if you live in one of these 3 words, no cryptography. But some of them, so these 2 are good for algorithm side, not for cryptography. This one is the worst of all because it's not good for algorithms and it's bad for cryptography. So we really hope we don't live in this world. Then there is the first word where cryptography lives in, and this is the word of minicrypt. That's why people call one-way function minimal assumption. This is the first word in which you have quantum cryptography, because one-way function exists, but the trapdoor one may not exist. What this means is that, for instance, you don't have that the factoring is hard, but one-way function still as an assumption exists. Maybe I don't know how to construct that, but I know that there is a one-way function. And so in this world, you don't have public key cryptography, at least in the sense that we know it. But you can still fundamentally have cryptography because you have the assumption of one-way function. Then in practice, you need to find a good way to implement that one-way function. But in theory, you can have cryptography. And the last word is called cryptomania, which is what we believe we live in for many years before quantum comes, that trapdoor one-way function exists, public key cryptography exists, and we're good. Right? So this is how it goes. You go from here to strong algorithms and to strong cryptography. Why I'm saying we don't know in which world we live in, because if you might remember, Arthur was saying this, that this is a belief system. Complexity theory is almost like a belief system. There's no proof about these problems being hard, or for a lot of them, at least for the major one that we care about, P is equal MP, there's no proof. There's a lot of evidence in complexity theory, there's no proof. So really, we don't know in which world, we still don't know in which world we live in. We have a lot of evidence that we're probably not here. And we know for sure that this is not a full picture, so we're not completely here either. We believe that this is this is the case. So, or at least this was what people believed till a few years ago. So this picture was a valid picture till a few years ago. Then it turned out that in the quantum world, this is not the case. Even this picture is not a good representative of all the possibilities. There's a weird possibility here that there exists a world that even if P is equal to NP and there's no classical cryptography as we have established it, there's a still possibility to do quantum cryptography. And this is not necessarily, like, there is still possibility to do quantum cryptography in the complexity theory sense. Like, this is different from, you know, QKD that you can do, like, you know, share a secret with some assumptions and stuff. And this result was done in 2019 by Kressman. And so let me tell you a bit more, but what this does to this picture is that it creates a new word here, which people call microcrypt. So microcrypt is a word where there is no one-way function, so there is no classical cryptography, but there is a still quantum cryptography. So let me try to tell you why this happened and what is the, like, you know, what's the reason that this word exists. Okay, to tell you that, I need to talk about pseudo-randomness. So we talked a lot about randomness. Arthur talked a lot about randomness, how you can extract randomness, how you can fundamentally using quantum extract randomness. So we know that quite well. But like classically, for many years, we kind of knew that you know, creating true randomness, it's almost impossible, and like even getting very close to a good randomness is like exponentially hard. So you need to put a lot of work to get like true randomness. So true randomness is a Platonic thing. But people in classical cryptography, they realize that if you have one-way function, you can construct things that are sort of random meaning like you have pseudo-random number generator. So pseudo-random number generator creates a string, which I know it's not completely random, but it's almost random in the sense that I cannot tell really that this is not random. So this is like pseudo-randomness. Or pseudo-random function. So I have a set of functions that when I sample from, this is almost as good as a truly random function, but this is pseudo-random. And what it means is that these look random to someone who is computationally bounded. So the person who interacts with these pseudo objects, if they're unbounded, if they can look at all the possible outputs, they can take all the computational power in the world and do exponential operation, they can actually distinguish at the end. But as long as they cannot do that, they're like normal people, computationally bounded in polynomial time, they cannot distinguish. So these turned out to be really, really useful. And whenever I needed randomness in cryptography or random functions in cryptography, which is all the time, because really you cannot do anything without randomness, then I could like swap that true randomness with this pseudo-random stuff, and my protocol will work in the computational regime, which is what I wanted, which is the reason I really needed one-way function. But quantum really, apart from, you know, giving you a way to extract true randomness, it gives you a different type of randomness. What is this randomness? This is the randomness of distribution of quantum states. So if you want to distribute, like if you want to sample a quantum state completely at random, there's a way for it. It's called sampling from something called Harmager. So it has this fancy name. So what Harmager means is that I think the best way to talk about this is graphically using blockosphere, my favorite object in the world. So this is a blockosphere for a qubit. And when I say I want to sample states at random, what do I really mean is that I want the state that I sample, if I draw them on the surface of the blockosphere, they should look uniformly random, right? So I want to be able, like, I want my sampling to be almost like equiprobable for all the state, if you want. And the way to do it is to sample a stuff according to this geometry, so that it covers my blockosphere uniformly. Now, what is this other ball? It's like, so this picture I decided in Mathematica for my, it's very old, it's from my undergrad project, but the project was this. So, you know, like qubits you can parameterize by these two parameters, right? So like, you know, okay, so this is a full state of a qubit, and there's like two parameters in here, theta and phi, right? So like as an exercise, you can say that, okay, so if I want to sample quantum states, qubits at random, one thing I can do is that I can randomly sample these parameters theta and phi from 0 to pi and 0 to 2 pi. So I sample this at random, it gives me a bunch of states, and this should be random. So if you do that, you get this picture. You'll see that they will kind of like aggregate towards the poles. And the reason is that I have randomly sampled, but not according to a uniform measure over the space of qubits. Yes?
Is this parameter the same one that we use in measuring?
Sorry?
Is this parameter the same one that we use in measuring?
Yes, yes. It's the over the unitary group, if that's what you mean.
This parameter is the one of the group. And when you're measuring the subgroup of the group.
So the measure, like the Haar measure, is defined over the unitary group of S. So it's like a measure over SUN. Yeah. So like if you want to exactly define it as that, but yeah. So basically, you're kind of like sampling all those unitaries over a set of qubit depth, and then you can extend it to multiple dimensions. But I think like visually you can see that this is the case for qubit. Makes sense? Okay. Yeah, so this is a fun thing that you do, and then what you realize, I think that the reason I put this picture, I wanted you to see it, is that in this uniform sampling that I'm doing in quantum, which is because, as you said, it's coming from a specific group, which is the unitary group, the geometry matters. And when I'm sampling these parameters like independently at random, I'm not taking into account the geometry. That's why it's not uniform when I'm sampling it like that. But if you sample according to Haar measure, then it will look like this. So it's true that. And so it turned out that this is a different kind of randomness. It's not like it's slightly different from like, you know, your classical distribution being sampled at random and things like that. Yeah. So we also know that in general, generating Haar random states are exponentially hard. So if you're doing this over n qubits, so you're in the 2 to the n dimension, being able to, you know, like generate this state or sample this state randomly, especially like generating any like random state, this is exponentially hard. Like it needs exponential computation sometimes. So similar to classical, where we had a true randomness that was hard to do, and we wanted to have like a practical randomness, we want to do the same thing here, because this randomness can be very useful. So if I want to approximate true quantum randomness, which is like randomly sampled according to Haar measure, there are in general two ways you can do that. So the first concept I call statistical approximation, or like a statistical pseudo-randomness. And this is the notion of t-design. So what it means is that you want to sample a bunch of states that on the first moment, second moment, third moment, up to the tth moment, they kind of like, they look like Haar random state. So this is the kind of like the statistical approximation. And then the more you increase the t, you get closer and closer to Haar randomness. But there is a different way of thinking about this, which is more similar to the way cryptographers thought about this. And this is like this computational approximation. So you don't want like your distribution to exactly look the same in the first, second, third moment, but you want this set of a state that you have or you're approximating to be computationally indistinguishable with the true random set, which is the Haar measure. So this is the goal here. So this is what we're going to talk about. So these are called pseudo-random states. You can have the same notion for unitaries. You can call them pseudo-random unitary. What are they? So pseudo-random quantum states or unitaries are a set of keyed state or unitaries. By keyed, I mean they're this finite set that you can index them. And they have two properties. They're generated efficiently, because that was the whole point of approximating. I want something that I can achieve efficiently. But they are indistinguishable to Haar random states or unitaries to a computationally bounded distinguisher. What does that mean? Let's see that a bit more. So you remember 2 days ago, I was telling you that There is some indistinguishability game that I will use it. This is the indistinguishability game. So you have a game where there's a distinguisher. You flip a coin, or like someone flips a coin, and there are two words. In one word, I give you m copies of my pseudo-random state. In the other word, I give you m copies of a hard random state. And the goal is for the distinguisher not be able to distinguish these two cases. If that happens, I call that indistinguishability. And now my bound is that this guy, they can do everything as long as it's polynomially bounded. So it's like in poly M operation or in poly time. And so yeah, but so you don't bound them on the type of things they can do, you just bound the power. And so what's very interesting, which was mentioned, so this concept has been introduced by Ji Liu and Song 2018, so quite late actually. And they show in the same paper that this is the computational version of the no cloning theorem, which is very interesting. I encourage you to have a look at that if you're interested. Which kind of makes sense if you follow what I was saying about, this like relationship between how well you can learn and how well you can distinguish. So it's kind of like related to that as well. But yeah, so this is related also to unclonability in a computational way. And so this seems like a very simple definition. You're just like, okay, I define something similar to pseudo-random functions, but just for states and unitaries. But you'd be surprised that this created so much research since like in the past like 6 years or 7 years or so. And it has been a lot of consequences in complexity theory, in physics, even in like very hardcore physics like quantum gravity and black holes and things like that. So it's kind of like surprising that has happened. But what kind of tells you that it seems like this notion of quantum randomness is really fundamental in nature, and you can do things with it that you cannot do classically. So it's kind of cool. So let's have a look at like a little bit more formally at the definition, because I think it helps. So yeah, similarly, we go again. So pseudo-random states, you can do the same thing for unitaries. These are a set of key functions. So this is the key space. You have a security parameters because we're cryptographers. So this is your family. So your state is one of the states from this set, which you index by the key. And then you want these two following conditions: efficient generation. So any algorithm that takes the key and spit out the state for you should be efficient, polynomial time. And then you want this to be computationally indistinguishable, which is the thing I was saying, to any polynomial time adversary using any polynomial time copied, as long as you kind of like mark them with M. So M can be any polynomial in blah, but when you set that polynomial, then the idea is that, okay, if an adversary, so the way you read this line is that if an adversary gets M copies of a pseudo-random state and spits out one, let's say it says that I'm in the pseudo-random world, right? So this event happens with some probability on average over the choice of the key. And if the adversary was given M copies of a hard random state, now the average happens over the hard measure and says 1, then the difference between these two probabilities, the probabilities of these two events happening, is small. Is negligible in my security parameter. So that's how you read this indistinguishability line. So again, yeah, sure. So this is that. So this is the reason that I told you. So let's go back just like a second to this picture. So pseudo-random states basically are the reason that this world exists. Because Kretschmer shows in this paper that, well, relative to some oracle, but still, we can live in a world that P is equal to P, so you have like no one-way function, but it's still possible to construct pseudo-random states. So the construction, like achieving a pseudo-random state, does not rely on having a classical quantum secure, but like classical one-way function. This is achievable in other ways. We might not know what those ways are, but it seems like there are. So it's like as if nature has a different path in achieving pseudo-randomness and cryptography out of that does not rely on anything else that we knew so far. So this is the reason. That's what this result says, that you can have a possible construction for a pseudo-random state that does not rely on one-way function, and that is true even it does not break even if P is equal to NP. Let's go back here. We've seen the definition, and so as I said, like this started a lot of consequences in the field, and so because it was very interesting, people have started to think about all kinds of pseudo stuff. So for instance, pseudo entanglement is a set of states again which are not very entangled, but they look entangled to someone who's computationally bounded. And remember, the key here is just like computational boundedness. It's not that they're statistically necessarily different or not. The key point is that I cannot tell. A polynomially bounded person cannot tell. And you can even have like things like magic, if like, which is a resource for like quantum computation. And I in general, I find it very interesting to talk about like or think about quantum resources in the computational regime, because this is a regime that is kind of like relevant in practice. I can give you a quote from Jens Eisert. He was like he was giving a talk about the pseudo entanglement or pseudo magic stuff, and he was like, yeah, we all die in polynomial time. So it's kind of true. So you do care about like polynomial time in some sense, even if you're not a cryptographer. So this is, yeah, kind of interesting to think about this stuff. So for cryptography, what this has been done, so okay, so you can achieve pseudo-random state, cool, but this is still not cryptography. All the interests with cryptography happen mostly with, I would say, this paper, like from the first paper as well, because they show a construction for private key quantum money, which is kind of like not nice and robust. It's like more interesting than the original construction of quantum money, and it's more efficient. So it's cool. But there was like not much cryptographic construction there. But then in this paper by Anna and Henry Yuan and Kian, they construct a lot of cryptographic primitives just using the assumption of pseudo-random quantum states. So they don't use like all this like previous underlying stuff. They only rely on pseudo-random state. So they show you can do quantum bit commitment. And by that, I mean, you don't break the impossibility, of course, but you know, you achieve like one-sided computational thingy. And you can do message authentication codes, which are important for authentication. You can achieve secure multi-party computing. And then there was this paper. They showed you can do digital signature. And so it goes, like there's a lot of paper, and like it kind of like blew up. But one thing is that even though you can achieve pseudo-randomness by Kirchner's result without one-way function, most of the constructions we know today, there's one that is not like that, but most of the constructions we know, they do rely on one-way functions. So the way I'm telling you how step by step you can construct this sort of like efficient, almost like random quantum state uses one-way function as an underlying part. You will see one of them in a bit. But yeah, so, and there's that. So it's still very interesting to look for the PRS that are truly pseudo-random from the quantum side, not like from the classical assumptions. And then everything gets so much more interesting and difficult for pseudo-random unitaries, even though they look very similar. So they're just saying, these are states, these are the unitaries. They should be very similar, but till last year, this problem was still open. Like there was no construction for pseudo-random unitaries. The one that we thought it worked, they were not working. And last year was this paper by Fermi Ma and Robert Wang. And so before that, there was like a paper by Tony Metteger and like these guys and Hen Yuan. So they kind of showed a construction for pseudo-random unitaries. There was a small gap, like there was like a specific thing which has to do with adaptivity. If you remember, I told you everything is like more difficult with the unitaries because you have the choice of like querying what you want and you can do adaptive attack. So this was not working with adaptive stuff, and then they like lifted it to. So it's the same construction that's been lifted here, but now they proved that you can even do adaptive and it's secure. So it's kind of cool. I was also working on that, but I got the scoop. They were faster. so yeah, this is about like that. But still the fields continue because there's a lot of things that's not like answered, and it's quite cool. So let me show you one construction of pseudorandom states to just like tell you that these are not very sci-fi, and it's quite simple. So the way you make a pseudorandom state, the most easy way, you pick n qubits, put them all in state 0, and then like apply a Hadamard on all of your qubits. This is like a building block of many quantum algorithms. Put everything in superposition. Cool. It's then on this like all superposition state, you apply this like magical box, which like kind of like applies a unitary of a phase. So this is like a phase oracle. So it applies like a function in the phase of your state. So what it does is this. So you give it uniform superposition. It gives you uniform superposition with the relative phase that depends on the outcome of the function. And this is where your key is used, right? So, you know, for every different key, you get a different function, you get a different state. And so now this set is the set of your PRS. Yeah, so now if the f is a truly random classical function, so it's a truly random function, classical function, like a binary thing, then you can show that this is a PRS. But this is not very interesting because that's not efficient. So this is not a construction yet. It doesn't satisfy my definition. But now if your f is a PRF, is a classical pseudorandom function, then this whole thing is a quantum pseudorandom function. Pseudorandom state, sorry. This is a PRS. So how does the proof goes? I can maybe do it on the board, like not the complete proof, but to give you the idea. So the important thing here is to understand every time I want to do such a proof, every time I want to show you indistinguishability, which is this thing I want to show, I'm not dealing with one single state. I'm dealing with an ensemble, right? And so the goal for me to prove indistinguishability is to show you that the ensemble of this state is computationally indistinguishable to the ensemble of the same amount of a state I get if I sample them from random, right? So basically what I'm interested is this expectation value, is this mixed state I built using getting expectation value over my random state. So this is my random states, right? And well, Haar measure is like a uniform measure over the unitary group, blah blah blah. So you can write this expectation value as this like sort of like integral. But the cool thing is that you can construct this average, and in this ensemble you can treat it. You can treat it as a state, as a mixed density, as a density matrix, which is this guy. Okay, so let's just write that. So this is the first ensemble. So I'm interested in this expectation value over random of m copies of these states. So these are psi of mu. Oh no, sorry. Because remember, you give m copies to the adversary, right? To the distinguisher. And then you can write that as this integral, but I don't care about that right now. So let's just call this rho of mu. So I claim that this is still a density matrix. Then you have like a different ensemble, which, so the first time I constructed it based on truly random function, right? So let me just like write that as well. So now I have a different set. These are my psi of, let's say, call them F. So this is, But then I take my average over what? Over like all functions in my family, right? So this is a all random function of the certain size. So it just like index it by f, but this is over like the space of all the functions. So I call that row of f. This is also a density matrix. Then I do the same thing for a pseudo-random function. So this is now a psi f of k. So now this is keyed, right? So now my pseudo-random function, this is like a limited set of the functions that look almost like random. And now my average is over my choice of key, right? Makes sense? So I call it row of k. And the way the proof goes is that because it's hard to jump. So what I want to show is that this ensemble look like this ensemble, right? But it was kind of hard to show that in one go. So they use a trick that cryptographers usually use a lot, and it's called hybrids. So hybrids is these things you create in the middle that are easier to show. So you show like, okay, this is similar to this, and this hybrid doesn't mean anything. It's not the solution to your problem, but it's just like an intermediate step for you to get there. And for them to get there, their intermediate step was this truly random function. So the first thing they do is that you show these two density matrices, they're closed. They are closed in trace distance with respect to our security parameter. So these are like the trace distance between these two, and that's the cool thing. Like this average over the ensemble, you can just treat it as a state, and that's like the key to this whole proof. So you show that this like trace distance is a small, or it's kind of like a small in the security parameter, so you can like make it okay. Okay, then so okay, how do they do that? I'm not gonna get into the detail because it needs like analysis of expectation values over the harm measure. So you need to like know a little bit about the harm measure and like what are the properties and how one can like calculate expectation value over that space. But you know, this is like some technicality. This is how we do it. But you do that, and then you show that okay, that expectation value over the harm measure is close to this. If you take this like very simple superposition state with the phase, and then you put like random function on top of it. Then they show that these two guys, so if I have basically this state when this is a truly random function, and then when I have it when this is a pseudo-random function, these are very close. So this is quite intuitive, right? So the trace distance between row of f and row of k is also very small, and this is easy to show. It's just like this computational thingy from pseudo-randomness that I use. So this is like, again, negligible in k. And this is also in m. So k, m also like this number. Oh, shoot, I forgot that. M also depends on k. So this is the k kind of like refers to the size and also the number of copies. And so now this is now very easy because these are distances and they're well behaved and they're cool. So by just using property of the distance, now the distance of row mu and row k, which is the guy I wanted, is also small. And you remember I was saying that the trace distance is a measure of distinguishability. That's it, because now if they're close in trace distance, what it means is that I cannot distinguish them. And if kind of like my probability of distinguishing it depends on this distance, and if this distance relies on this like negligible parameter in my security, then I have indistinguishability. So it's like the steps are really like easy and intuitive. The hard work, I think, it goes into this first step actually, when they show that like something you sample from harm measure is close to these kind of things. But yeah, so that's how you use the very simple tools like trace distance and indistinguishability in a very sophisticated proof. And so this is a construction. You have the proof, and it's quite nice and easy. Not the problem, but the shortcoming, as I was saying, of this construction is that you realize this relies on pseudo-random functions, right? So pseudo-random function on their own, they rely on one-way function. So this is not that true construction that gives me cryptography without relying on one-way function, but it's just like, it's good enough for practical purposes, but if you're looking for that one, we still don't have it. This is not that. But this is the building block of a lot of like these things, like pseudo-random stuff or pseudo-entanglement. So yeah, so I wanted you to see that. I think this is the, what am I saying? Yeah, okay, that was the bottom line. I think this is all I have, or I have more. No, I have more. Before I go to hardware assumption. Okay, so this was pseudo-randomness stuff. And this is not the only minimal assumption though that you have in quantum cryptography. And you know, like these things that you can build cryptography on top of. There are other examples. One of them is this, like, so I'm not gonna get into detail that much, it's just like tell you that what are the things that exist. So there is this concept called EFI pairs. It was introduced in this paper, and EFI stands for efficiently generatable, statistically far, computationally indistinguishable. It's exactly what it is. It's a pair of states. It's a pair of states that are that you can generate them efficiently. So far, this is close to pseudo-random state, but then you specifically say that these two states are statistically far, right? So these are the things that if I write them down, I can like know that they're statistically not the same thing. But if I just give you the state, they're computationally indistinguishable. So it still is a notion of computational indistinguishability, but like put in a different way. And so why they're important? Because, and this is very important, because out of EFI pairs, you can get quantum bit commitment, like kind of like the best quantum bit commitment you can possibly get. And so you can get one-sided, computationally binding, but statistically binding. And well, out of that, you can get multi-party computation. So this is a pathway to do cryptography just by relying on such a thing exists. And not relying on anything else, not relying on any one-way function or anything, just by relying on existence of this pair. And so then the story goes on, and actually David has a really cool paper and manual on this. And so what they show is that you remember I told you this like pseudo resource, you can also have like entanglement as one of these things. So pseudo entanglement is also like a set. They have low entanglement, but they look like the ones that they have high entanglement. So what they show is that these two assumptions, one of them being pseudo entanglement and one of them being EFI, they're related in this nice way that if you have pseudo entanglement, you can get EFI pairs out of them. And it's like, to be able to get that, this is necessary. So it's like, you know, it gives you a hierarchy of things. And then there's this other paper by Alex Grillo and my friend Alvaro in Sorbonne, and they showed that you can do that with any pseudo resources somehow. So you cannot get EFI pair, you can get something else that's almost like EFI pair, but the importance of the story remains the same. And the importance of the story is that out of this like EPFI pair, which is different from that, but kind of like similar, you can still get commitment. So either you have pseudo entanglement, you get EFI pair and you get commitment, or you can use any pseudo resources, you can use their sort of framework, you can get this thing in between, and then you can get quantum bit commitment on top of that. But these are ways of like going from these resources to what we care about, which is cryptography. Questions so far? Because I think it's a good time to stop and reflect. Yes. No, there's a difference. That's what I was saying. So this is a slightly different. This is EFI, but pairwise. That's what the P is like. So there's like there's a pairwise notion in the EFI that they have in their definition. But yeah, it's different from EFI. So it like the reduction doesn't go from this to this to this. It goes from this to this like new thing to commitment. But still, you can get commitment, and it's kind of like nice. Because what they say, that's what the title of the paper says, because out of commitment you can get a lot of cryptography, is that like any of these like pseudo resources, if you use them in a right way, it can give you like that thing you need to do cryptography with. So that's cool. And so these are minimal assumptions, right? So like you think, okay, I told you about EFI, pseudo randomness. Should be it, right? It should be like that. The landscape is really nice and beautiful and easy in quantum. It's a mess. So this, if you're interested, there's this thing that Orsata has created in his website. It's called microcryptsu. So it's kind of like all these assumptions and intermediate things that people in quantum cryptography in the past 6 years or something have created, and all their relation, like what implies what, and like how we can, and it's kind of like it's getting insane, because like every day you open the archive, someone has come up with a new assumption, and it's like it was really hard to keep track. So thanks to Orda that he put them all together so that we can know what relates to what. Like for instance, you can see some of the things here. So this is like EFI, and EFI implies quantum multi-party computing. EFI implies a statistically binding quantum bit commitment, and well, there's like, this is pseudo-random states, and pseudo-random state, yeah, you can like do them with one-way function, but like you don't have to. And there's like a big chunk here, which I did not talk about and I won't talk about, but it's just so you know that like, what I wanted to tell you is that this picture should not be this complicated. This is because we're trying to relate this assumption and understand this landscape. I feel like once we understand, there will be like really minimal stuff that things will rely on them. And I think that's the goal. That's why people like keep exploring this till this clarifies. But it's very cool. So there are things that happening here that it can happen even if like you chop off that bit, so you don't have one-way function. And this is the point you need to know. All right, so I'm gonna switch to a different topic. I think if you want a break, this is a good time. Should we go for a short break? Okay, like 5 minutes or something, and then we're back. You ready for a different way of doing cryptography? So you've seen how you do from one-way functions to the randomness. So these are there. Now I'm going to switch to something else. And that something else is that, can I do cryptography based on some assumption that I make about my hardware or the physics of my hardware? And when I say like assumptions, I don't mean that quantum mechanics is true, because that is also an assumption that we make, but that I'm not like counting as an assumption so far. So it's kind of like a broad assumption, but like, you know, more assumption on the hardware. Like, can I assume something about like this device that I'm having, and it's a reasonable assumption, and if I do that, does that bring me anything interesting for cryptography? And this is what I want to talk about. So just to give you a perspective, this field is not so big. It's a very niche field. Like quantum hardware security or quantum hardware assumptions is not very big, but there are different class of things that you can count as hardware assumptions. So today I will talk about this, which I have worked on a lot. So quantum physical and quantum functions. So I will like explain this in detail. But I just wanted to show you that there are other things that you can count as hardware assumption. For instance, you can have an assumption that you have a part of your device, or let's say part of your quantum computer, like a very like particular region, that you just trust the execution of the things that are happening there. So this assumption also exists classically. People call it trusted execution environment. So you can assume something like that quantumly as well, and this is counted as a hardware assumption, and it allows you to do some stuff. For instance, it allows you to do delegated quantum computing, verifiable delegated quantum computing, like efficiently, and there's some no-go that with no assumption, with no communication and no assumption, you cannot do that, but like this allows you to do something like that. Then there are things like one-time memory. So some, let's say, quantum object that you can only interact with once, like you can input something on it, but like, you know, you can just like, you can read it once and that's it, and something like that. There are things, and there's like one-time memory, you can also construct some interesting stuff out of that. You can, so we know that quantum hardware is noisy, so there are models that formalize this as a hardware assumption, so you can like assume, which is kind of like a very reasonable assumption, to assume your hardware has like some amount of noise, and like you're in this regime of like dealing with storage models that are noisy, and this turned out to be also like a nice assumption to do some cryptography on top of. So there are other things as well, but I will talk like specifically about this. So what is physical unclonability? So we heard a lot about like unclonability in quantum, right? But there is somewhere unclonability in it that's quite different from the unclonability we have in quantum. That in physics, so this concept of physical unclonable function, they were emerged from electrical engineering. Was that people had like some electrical circuits that were produced, let's say, in a factory, but so they were the same, so like copies of the same circuit, right? But then they realized, okay, there's like, I can kind of like play around with the circuit, and there are like some maybe specific places in the circuit which I can apply some voltage, and I can read out like something that comes out of the other side of the circuit. And whenever I do this game, I see that there's like the thing that comes out of the other side as the outcome of the, like, let's say, voltage or whatever. I'm not an electrical engineer, so if I say something nonsense, don't pretend to be. But yeah, so it's like there's some sort of like input in terms of like voltage, and there's some sort of output in terms of voltage that you read out of your circuit. And whenever you do that, they realize that this is quite unique and it's different from device to device. So they were like, okay, so this looks like, even though when I'm really trying to make exactly the same hardware, there is a difference, and like there's a unique fingerprint in the device. And the only place that this emerged. My favorite example, the way I usually like to talk about this, is through optics. So the idea is that, let's say you have a factory, and this factory produces crystals, and these crystals, in all the macroscopic properties, they're exactly the same. Like it's like a factory line, and it produces crystal 1, 2, 3, 4, blah blah blah. But if you have a good microscope, and if you look at it like close enough, you will see that these are not the same, because like the shape of the crystal inside is quite unique. And the reason that this happens is that I have no control when I'm manufacturing these crystals on the exact positions of like this like underlying microscopic structure. Like I have no way to impose that, and I have no way to control that. It just exists because of the physics. And so now, okay, so this is interesting, but can I use it in any way? And you can. One way you can use it is that if I shine a light to this crystal and it gives me like a scattering pattern, this is scattering pattern. If this is the case, from one crystal to another, it's very different. So it's quite unique. It's like that voltage thingy that in the electrical circuit you would read. So it's quite unique. And if you let's say make a database of all this scattering pattern, then you can uniquely identify these devices by this like scattering pattern. So it's almost as if like this device has a unique fingerprint. And so the way you can think of it is that you take this crystal as some sort of function, that it takes some input, which is in my example the light beam. So you call that challenge, and it does something to the light. For instance, it scatters it, and it produces an output, which we call a response. And so okay, before I go, so then this like unique behavior that you capture only by interacting with this device, this you can use to do cryptography with. Because if you think about it, this is almost like a key, but it's like a physical key. So if I have this like information, I can like use this key to open stuff, and if I don't have it, then I like know this information somehow. And so this was there in the classical world, and one would think of, how about the quantum? Like, can you have something like that in the quantum world? And you can. So this is something that I worked on. So the concept, like this concept, you can formalize it in the quantum setting, and you can have some objects that we call quantum physical unclonable function. And the idea is quite similar, except that now this object is, so this was a map, right? So if you abstract this from the hardware to the software, this does something to your inputs. That's why it's called physically unclonable function. So it's some sort of function. And now in the quantum world, your input is quantum, it's like states or things like that. And your map is a map that, you know, transform this quantum object to another. So it's like a quantum map. It's a channel or it's a unitary. But the cool thing about bringing this concept to the quantum is that if you take the optical example, this is actually, it can be very well be a quantum physical unclonable function, because then you can interact with signals that are quantum. So you still interact with it as like lights, but then you can have signals that like they qualify as quantum states. and then you can also like do some like, you know, measurements that you experimentalists know better than me in the quantum optics. So you can like detect these like outcomes as quantum states. So it's almost like the same device, but a different model and a different way of interacting with it. And if you interact with it differently, it gives you a quantum object. And I think this is quite cool. But the whole question is that how you can use this to do cryptography, and why the hell this is useful. Okay. So this is good. So in order to tell you why this is useful, I will do as any cryptographer will do, I will break it. So first, let's break the classical physical unclonable function. How do you break such a thing? So remember, what this was, it's a device. And this device is like a black box, right? So someone gives you this black box, you can interact with it, you can challenge it, get the response, challenge it, get the response. And it's supposed to be, so what is this functionality that I want from it? It's supposed to be unclonable. Ability, if you remember my first lecture about maps, means that you should not be able to reproduce the outcome that it's reproducing, right? So if this is unclonable, it means that I can give like you this crystal, and as long as you have it and only you have it, there's no one else that can produce this like responses. Let's go back. So these responses that I expect for this device to have. But if it's clonable, or if it's forgeable in some sense, what I can do is that somehow I can make another copy of this, and then I can also pretend to be the guy that has the same crystal. So it's like, it's a bad key if this happens. So the property that we want to preserve here, or we want to have here, is this like unclonability. So how do we do it? How do we do this? How do we break it? Yeah, so that's exactly how you look like when you break a protocol. Trust me. So the way you break it is that you say, okay, so I'm allowed to interact with it, right? So you give me a black box. Okay, I take your assumption. You tell me that this has been generated through a process that I cannot control, and I cannot manipulate. Like even the manufacturer of the crystal could not make exact same copies. So how would I be able to make the same copies, right? So I take your assumption, that's fine, but you give me a black box, and I can still interact with it. So what if I interact with it and I get a bunch of these pairs? So I get a bunch of input and output. So I call them like this database. And then I give this database to a machine learning algorithms, and I'll be like, okay, you know, extract a model for me. And it does. And if the quality of this model is good, if it predicts as well as, you know, like the function is supposed to be, then it doesn't matter that I cannot copy the hardware. I can reproduce the outcome. So in a sense, then you can think of it as I can make as many copies of this function as I want, because now I have a model that predicts the same thing that this would generate, right? And this is exactly how you break the classical path. And people have shown, like, after this was out in like the hardware security community, some people attacks on them, and the machine learning attacks work really well. So the stuff that looked very unpredictable and very like cool to do cryptography with, they all broke down. They were like, okay, this is learnable, so it's not unclonable. And this is like exactly that link that we're looking for. So the question is how to formalize this in a quantum setting and how to get security that you don't have. So in classical, again, so you can't take this assumption. We know that most of the times it won't work. People are still like, this is still an active field because people are working on different ways of maybe being able to construct these devices that have this like behavior of unclonability and stuff. So for practical cryptography, this is still a valid field and a lot of people work on it. And for me, who's a theorist and like foundations and stuff, this kind of things a lot. I'm like, that's not really interesting. I want something that I can prove. Like, I don't want to be so heuristic about, like, even if I take an assumption, I want to be able to prove something about it that I can trust. And so that was the idea. So what is the minimal, like the most minimal thing I should assume so that I can get the functionality of physical unclonability? And this is where learning theory or learnability and cryptography, specifically with this like functionality that is called unforgeability and unclonability, they link to one another. And at the core of these things, which again, like if you remember like my talks from 2 days ago, it should make sense that the core of these things is this notion of black box. This is the unknownness of this thing is exactly what gives me unclonability. It's the same thing that gives me unforgeability, and it's exactly the opposite thing of learnability. So this is what we are going to rely on. So what I'm going to rely on is that whatever my unclonable device is, it should be an unknown unitary. And unknown unitary, I can define it formally. I can say, okay, I call an unknown unitary something that the first time I interact with it with a random state, I cannot know that the outcome is a random state or it's coming from my device. So for instance, this, if you give me a quantum circuit, I can look at the quantum circuit because this is not a black box anymore. It doesn't matter how, it's not a black box. So it should be a black box. It should be an unknown unitary. But if I have an unknown unitary, I can kind of like think of the same sort of attacks that I do here on my unknown unitary, right? So I can assume that someone has pairs of input and output of this unitary. Then the adversary now, that can be a learner or like any algorithm they want, but you know, like one of the good algorithms that you see here is learning algorithms. And if they run that, what I don't want to happen is that when I give a new state, the adversary gives me an outcome which is the same as the actual outcome or is close. I mean, I don't expect to be the same, but it's close to the actual outcome, right? So remember we saw exactly this thing. This was a learning problem, right? So what I'm trying to do here is to show that an unknown unitary with the assumption that the way I will like define it, it's unlearnable for a quantum polynomial time adversary. So if I manage to prove that for unknown unitaries, I've proven something that you cannot prove classically. You need to just like rely on the assumption that this hardware is such and such. But here in the quantum, the difference is that if you take this a step and you can prove it, then you have a physical unclonability that with respect to the assumption that it was an unknown unitary to begin with, it remains unknown. So it remains unlearnable. And well, you can do that. So again, going back to the definition, this is just a map from quantum inputs to quantum outputs for the easy construction, because it needs to have also some robustness properties and things like that to be able for it to be interesting. We assume that this is a unitary for now. So you can extend this to quantum channels, but let's stick with unitaries for now. So if this is a unitary, then you can show that you can actually prove that this satisfies unforgeability against quantum adversaries. So this is like unlearnable for any polynomial time adversary. And well, I can't have a minimal hardware assumption because this is the least thing, like, you know, you giving me a hardware that the only thing I ask you is that I don't know what this hardware is the most minimal hardware assumption you can possibly ask to achieve unforgeability. And the rest is provable. It's not like you don't just assume. So then you can achieve that. And so, like, similar to what I've been telling you, that like it's like people are obsessed of linking these assumptions to one another. I also did the same thing. So we showed that this is kind of like connected to pseudo randomness, which makes it very interesting. So it's like this unlearnability, which shows itself as like, you know, physical unclonability. It's also related to that like quantum pseudo randomness that's come from the randomness that is coming from being able to uniformly sampling quantum states. So these are also related. So basically, if you have a family of physical, like unclonable functions, that can act for you as a pseudo-random unitary. Almost like you can get pseudo-randomness from somewhere else, from hardware assumption, not from one-way functions, for instance. And so, so that's for the foundational part. But for the practical part, you can now use that for cryptography. The most useful thing you can make out of these unclonable functions is authentication schemes or identification schemes. So most simple protocols or most intuitive one are like this. We are two parties, right? So Alice and Bob, we want to identify one another, or you can think of it as there is Alice, who is the verifier, is this like big server, and Bob is like a small device, it's like a phone, right? So the way it goes is that the one who needs to be authenticated has this unclonable device. So this guy has the puff, and this guy has a database of some of the talent and responses, so input and output. Like, I don't need to have the full description because that would be exponential. That's like not reasonable. And I don't need that. I need like a small database of like some of this input and output. And so what I do is that, so remember here, this is a quantum physical function. So the input and outputs are quantum, the state. So whenever I want to identify Bob, I send one of these challenges over the channel. And the only thing that Bob does is that it like sends the challenge into the device. So if this is a light that I'm communicating, just like Bob put the device in front of the light and waits for the outcome to be generated, right? And then Bob gets the outcome, put it back. Then the hard part is here. So I need to be able to verify that, right? But so you can imagine if I have the description of this state, the verification is quite easy because I just measure and look at it. If I don't have, and I only have quantum state, this is a bit harder, but it's possible. So there are things, who knows what swap test is? Okay, some of you know. Okay, so swap test is this like very simple algorithm that allows you to check equality of two unknown quantum states. So if you have two quantum states that are coming in, this algorithm, what it does is that, you know, it does like a controlled swap gate and something else, and then you measure, and it gives, if these two states are equal, it gives you with probability 1, which means that they're equal. If they are different, then you have a one-sided probability error. So if they're not equal with like some probability, you get the wrong answer. But if they're equal, it gives you the equality. So you can use swap tests or generalized versions of swap tests to be able to do this check. So this check is possible. So remember, again, in cryptography, it's not just important to obfuscate, it's also important to be able to verify, and this is the hard part. So you can verify, and the protocol goes, it's quite intuitive. You can have a less intuitive version of that where you assume that you don't want to do this verification here, so you kind of like want to push the hard part to the other party. And this makes sense in a scenario where now the low resource party wants to identify the server. Can also do that. I'm not going to get into the details of that, but that's like slightly more complicated, but it works. So these are now protocols that just relying on the fact that I have this device that in single shot is, you know, I don't know what it is, so it's a black box. Then I can prove that these authentication schemes, they're exponentially secure, meaning that they're secure against any QPT adversary with a with a probability that is exponentially small. Yeah, so you can do that. So yeah, this is kind of cool, right? But what's the bad things about it? So I'm gonna tell you all bad things about my protocols. So the bad things about it is that, well, so first of all, so this is an assumption. As long as I work with it as an assumption, it's fine. Like PRS and everything else, you can just work with it. But as soon as I start getting into something constructive, like I come to one of you guys and tell, can we implement this protocol? The first thing you ask me, okay, give me the puff. And I'm like, okay, I don't know how to make that. So, so that's an issue. I told you there's this optical stuff you can use as a puff, but that works in practice. But this is not so easy to be able to have a good confidence that they satisfy all the properties that I have. So I need to do some statistical tests on them to be able to certify that. So that's still the best possibility. But still the construction is not so trivial. And the worst problem is that this protocol, because I really need to work with databases of quantum states, because I want to keep these input and outputs in a quantum form, means that as long as I'm doing this authentication, I need to keep this database alive. And this database is a database of quantum inputs and quantum outputs of large dimension. And this is really challenging to keep that in current quantum memory. So as long as with quantum memory, this is a pain. So when I go with that protocol to an experimentalist, they will shoot me in the head. So they will come back later. Fair, for good reasons. So there's also some generalization of this that I wanted to just to show you, to tell you that this link between learning and unclonability, especially in the sense it continues. So you can imagine that well, in a realistic world, I don't have a unitary bypass. I probably have a noisy one, and so exactly because here it's a pain to keep these quantum states in forms of the state. What if I keep the statistics of what I measure after that? And so there was a proposal of a puff, and I was okay, so let's say I select a random unitary like this, which is a series of rotation gates, and there's not even entangling gates, so it's just I just keep this unitary, and so the only thing I do is that I assume that now this is noisy, so there's some level of noise here, and this seems like it's a good idea. So the way I work with it is that I only keep the challenges after the measurement. So now I have classical challenges, which is good. It makes the protocol easier to implement. The problem is that in this paper by Anna Papa and Nicholas and Jean-Pierre Siffert, they show that if you have a puff like that, then you can actually do this cryptanalysis by machine learning, and even the learning algorithm is super easy. The users, I think it's just they use simple regression, but then they show that this can be broken. And well, you can think of that. Okay, so maybe this circuit is too simple for a puff. Maybe this is the problem, right? Maybe the problem is not that I need to keep the states as quantum states, but it's just that this is too easy. So you can extend that, and this is what we've done. So you can say that, okay, so assume in general you have a very, very general quantum circuit, and I'm just changing the access model to make things nicer in practice. So the only thing that I'm changing is that, so this is still a circuit that can be as complicated. It gets as input quantum state, but it spits out a classical value, which is this expectation value of some observable that I like to observe here as my output, right? So I define my output with respect to some observable, take the expectation value, and that is my output. So now, if you work with this model, which looks nice enough, you can show that there are learning algorithms that can break this in a lot of time, even if this guy is a Haar random unitary. So even if your circuit is super complicated, as long as you only work with this a statistical outcome, And there are like some assumptions that needs to be satisfied. It's not like in full generality, there's some stuff about your observable as well. But under certain circumstances, then I have an efficient learning algorithm that can learn this like complicated process. And so what we show in this paper that like you can actually do that, and this is like a general attack on all these kinds of like physical unclonable functions. There's a catch though, as I said, there are like some assumptions on the observable and stuff like that, which, you know, like it leaves some hope for like this class if you're interested in like doing something with that. Yeah, but it's kind of interesting. Like every choice that you make about like what is it that the access model and things that I'm working with, it has a consequence on your security because it can tend how effective the algorithm is. And if you can learn it, you can break it. Right. Okay. So this was that. But now the idea, so I showed you all the bad protocols. You're probably asking why she's doing that. Like, why are we studying this? This seems lame. So is there any good protocol? And I want to show you that there is. So there is a good protocol that is secure. It's like actually surprisingly easier than the ones I showed you. It kind of like follows the same ideas, combines some ideas from QKD, which you learned about, and it achieves authentication in a nice and efficient way. So the protocol, it works with a scheme or like a construction, which is not a quantum puff. So the quantum puff is this like, you know, unitary, this object is very secure, it's very cool, you can prove unforgeability for that, it's secure against like all kinds of quantum adversaries and stuff. But I'm not building my authentication protocol based on that. So I'm going to build my authentication protocol based on something else. And that something else is a classical puff, which I know is bad, and that's important. So I know that there's a large probability of this classical puff being broken, but I still want to work with that. So, you know, kind of like Arthur was saying yesterday that you have this like, bad randomness and you want to get good randomness out of it. So it's kind of like what I'm doing. So I'm gonna work with a bad source of randomness, but like my randomness now is a physical unclonable function. And I'm going to make something good out of it using quantum. So the way it works is that this classical puff, let's say from like, you know, I model it classically as a function. So it takes as input a bit string, it's as output, it outputs a bit string, right? So what I'm gonna do is to very simply take 2 bits by 2 bits as outcome and do our beloved BB84 conjugate coding encoding, right? So I'm just gonna do like encode the outcome inside this quantum state. So now this box takes as input classical input and it spits out quantum input. Well, this quantum input is not as nice and general as the one that quantum puff outputs, because these are like single qubit, this is like separable form, so you know it's all that. And so okay, before that, and this, if you just use that, this is not secure enough. And this is still better than the classical puff. So if you just use the classical puff in a protocol, it breaks very easily. If you use this inside your protocol, as long as you don't allow the adversary to issue any query they want. So if, let's say, adversary just sits on the channel and looks at the messages that is passing back and forth, as long as you do that, this is enough. This is secure. But we don't want that. We want any QPT, like we want security against any adversary, like any polynomial adversary. So this is not good enough. We still need to do some work. And this is how you do the protocol. So we call it quantum lock. It uses this box as a subroutine. So this box is that's there. But in order not to let the adversary query whatever they want, we implement some sort of check on both sides, right? So in the normal version of the protocol without the lock, you send a classical bit string. This guy produces this like quantum bit string and sends it back over the channel. So this is the plain version of the protocol. And here, what the verifier does is that they just go look in the database, they look at the, you remember how Wisner quantum money was being verified? This is exactly the same thing. I look at the database, I read all the outcome, measure in the right basis, check all the outputs, and as long as it passes, right? So it's kind of like that verification. The problem with that is that if I allow the adversary to sit here and be able to query the box, because in some sense they can, because what if the adversary pretends not to be the Bob, but to be Alice? Then they can send me query, and I don't know where these queries are coming from. So I still reply, right? So I still reply with the correct ones. But the problem is that because these are like, these qubits are 1 by 1, right? So let me maybe write it here. Okay. So what did I do? So let's say I'm the adversary and I query with some X. This is the hybrid puff. And it gives me, let's say, this sequence 0 plus minus 1 0, right? So what I'm gonna do is that next time I will query it with exactly the same thing, and it will give me exactly the same thing. So now the problem is that if I query this a couple of times, what I end up with is these copies of states. Let's say I have 4 of them now. I have 4 of the plus. So now with multiple copies, it's actually not hard to distinguish these things, because I can just, I can measure it in one basis, and then measure it in the other basis, and then the third time, use it as a check to see if I measured in the right basis. So with a couple of back and forth, I can know with a good confidence this is a state 0, and this is a state plus, and so on and so forth. And if I can read this sequence well, then I can generate this, like I can start being able to read the classical puff, because remember the point was that the classical puff can be broken. So if I have access to the classical database of input and output, if the adversary has these things, this classical database, it breaks easily, because I chose to work with something that's breakable, not something that's like secure enough, right? So I'm trying to boost this security. So you don't want this to happen, and for this not to happen, we implement this like lock mechanism. And the lock mechanism is basically that whenever I'm asking a question, I'm including part of the answer in my question. So I do the same encoding. So I pick half of the outcome of the classical thing, and I'm doing the same encoding, the same BB84 2-bit encoding that I expect to get as an answer, but just for this half. And whatever I'm like, when I'm sending this over the channel, I'm sending the full classical input, but half of the output. And what I'm expecting from Bob to give me is the other half of the output. Now, if Bob has the actual device, because the device produces this like other half, then it's fine. It's the same as like asking him for the full thing, right? It's not so different. And so I'm still checking Bob. But now, because I give him half of the answer, he can also check me. So he can check that this is a valid query. It's not about only valid responses, but it's also about valid queries. Now, when you implement this two-way check, then you can show that the adversary cannot query adaptively, because you kind of like break this adaptive query by implementing this check.
It's kind of like luck.
Kind of like what? So you have locking tracks as well, but not all the message authentication codes have that. Like they don't necessarily need that also. That's
what are like authenticating the channel or the person?
So it authenticates that's a very good question. So this authenticates, initially it authenticates the party. So it authenticates you as someone who has the device. So I know that I'm talking to the right person. So it kind of like authenticates the channel and the person. If you want to authenticate a message, you can do it with this protocol, but you need to do a little bit more on top of that. But in theory, you can do that as well. Yeah. Yes.
Can you prepend it to PKD like how you authenticate channel?
Yeah, exactly. So you can mix that with QKD, and that's like one of the applications. So you can do this for authentication, but you can also combine that with QKD, and yeah, so this will give you. So let me see. I think I do have a slide for that. Like, just wait 1 second. I'll get back to you if I. Yeah. So what are the properties of this? So if you do this, just to repeat, so you can get now provable security against like the most powerful adversary here. And so one thing that's cool, I keep telling this is secure against QPT adversary. And the reason is that you cannot never have learnability against unbounded adversary. This is in general true. So you keep it as QPT level because you assume at some point that this box is being transferred back and forth, right? And you don't want to assume that like that channel is secure. Like this is at some point being transferred between the two parties over an insecure channel. And in that stage, before any authentication protocol starts, the adversary can attack. And this is the reason I'm assuming the adversary is still, they cannot query this unboundedly. But the thing is that after the box is being transferred, I don't need to assume that anymore. So in fact, the security here over the channel is similar to QKD in the sense that this adversary is unbounded. They can do whatever they want. But when you talk about the combination of the whole protocol, then you take the weakest, thing. So you take the worst case, which is this like polynomial adversary. So this achieves security against unbounded here, QPT overall, and you can show that you have like good security. You can combine that with QKD, and the good thing about combining this with QKD is that it doesn't need any new technology, because I'm just sending BBA4 state for QKD. I'm also sending BBA4 state, so I'm really not asking you to do anything else in your lab, which is a good thing. Yes.
Well, this feels like I'm thinking in terms of QKD, right? So you have the QKD box on the right, and you buy it from the vendor. So you use the properties, the physical properties of the box to authenticate. But if you're buying the box, you can just come with a pre-shared key, and then you can authenticate with that, right? So what do you gain from this key compared with this?
So that's a good question. You're buying this box. Like, you don't need to, like, this part is just like simple measurements and stuff. There's nothing you can like really do with that. You're buying this box which has this part and the, what do you call it? Like the QKD preparation part. So you kind of need to trust that this box does what it does. So this is not device independent. I mean, I'm like telling you that this is hardware assumption. So I'm actually trusting the device, right? In that sense, this is true. This has no longer security against manufacturer itself. Like the quantum puff, it can have that, but this does not, because I'm trusting some sort of construction. But this is still better than a preset key in the sense that you can still like close this box, and there are like engineering way to do that, to have this like, tamper-proof boxes and stuff. So you can create this box once and close it, and then you have a nice way of like doing authentication, because then you need to just send this to the party you want to authenticate once, and for as long as you have the database, you can authenticate them. So
in that case, keys, but you also need to have they want to memory on the other side, right?
No, so that's the good thing about this compared to the one that I said. You only need, so this guy only keeps classical record of this database. So that's the good point, because otherwise, yeah, you needed to. So as long as you're happy to do the quantum memory, you can still work with the quantum puff, and it has like a less trust assumption, I would say. So it has a higher level of security in that sense. But because you want to do, like, we wanted to like build something practical, we were like, okay, let's get around quantum memory, and this is one way you can do that. Because if you also remember, my previous slide was telling you that just taking the measurement outcome is not enough. So that's not a good way of going from quantum memory to classical memory. But this is so this you can use. So this protocol has also a cool property that you cannot achieve classically. This is like a very quantum property, and it's the challenge usability. So it has this property that as long as the protocol doesn't, so as long as the verification doesn't reject, right? I can reuse my key, and this is something that classically you cannot use. Like, think about it. When I'm sending a challenge over the channel, right? And the other guy is sending me the response, then if the adversary is sitting here, the adversary sees the input and the output. So like this is full information. There is like I can never ever use that challenge again. So one problem with the normal like PUF protocol is that every time you use a challenge, you need to like hash it out, like take it out from your database. This is unusable, and so it means that because I'm not keeping a big database, after a few times, then like in polynomial time, I will run out of challenges. But the good thing about this protocol is that as long as you're using the protocol and the protocol passes, then you give this extra guarantee that you can prove using quantum information and exactly using the uncertainty properties and mean entropy and this kind of things that you use for QKD. You can use those properties to show that this allows you to reuse the challenge. So as long as the protocol passes, there's no breach, so you can reuse the challenge. And this is like a quantum advantage in some sense, if you want. Okay, so I have only one slide. I did not have a slide on authentication, so I'll talk about it now. So for authentication, this is actually like a nice way to combine with QKD and do authentication. Good stuff about it is that it's better than a pre-shared key in some sense, because it still like brings you more security in the sense of trust level. Although the problem, like the downside of it is that if you start with a small pre-shared key and do that like cyclic thing that I was describing, you're still in the information theoretic regime. If you use my protocol, you will downgrade yourself to a hardware assumption regime. So still your authentication uses hardware assumption. And as a cryptographer, you cannot say that this is not the case. This is the assumption you use. So in some sense, it will lower down your security. But if you're looking for like, something practical and reusable to be able to do this, this is a solution. And for some application, maybe this is a better solution than using the post-quantum schemes. There is actually like a smarter way to kind of like do key distribution and using this protocol, and we have a patent on that. So there's a way that you can do self-authenticated QKD. So you don't need to do this, then do the QKD. You can do everything in one go. So yeah. Unfortunately, they don't let me to talk about it yet. It's not out. So yeah, but there's a way to do that. Okay, so this is all I have to tell you about the hardware assumption. And I only have one slide to tell you a little bit about cryptography from learning. But before I do that, do you have any questions? Yes.
I don't know, maybe you said it already, but what would be like is there a straightforward, easy mathematical formulation for what security means here?
Yeah, there is. So here you can still formalize the security in terms of unforgeability. So now your unforgeability is for this box, for this like hybrid PUF. But you can still like define the unforgeability in the similar way. So unforgeability in your normal way was that if you see, let's say, a bunch of like a polynomial number of these queries, you're not able to give me the outcome, the right outcome for a new query. So this was like unforgeability. For quantum PUF and for this kind of PUF, you need to kind of like change a little bit the definition of the unforgeability to capture for like quantum attacks and quantum states. But if you do that, it's kind of like the same. So the definition, the level of unforgeability you would need to have is that if you've seen a bunch of the challenges, then if I give you a new challenge, then on average, this is hard for you to. So this is like an average case hardness that you need to satisfy. And that's enough. You don't need worst case hardness to be able to achieve these like protocols. So yeah, there's still unforgeability, and then you can quantify really nicely the maximum success probability of adversary doing that.
Is there some IID assumptions of the query?
Yes, there's IID assumptions. So there's IID assumptions in the underlying classical PUF. So the underlying classical PUF is bad in the sense that it produces strings that have bias. This is how we can quantify like PUF being bad, because a good PUF is almost like a random function, right? So it produces like this outcome. Oh, one thing I wanted to say that I forgot is that there is a big difference between random number generator and a PUF, because random number generator is a random process. Like we can think of it as a box. Every time you push the button, it will give you a new random number. A PUF is something that when first of all, I don't push the button, I put some input. So every time I put the input, for the same input, I want to get the same output. So it's a very deterministic process. But the randomness is in the unpredictability, is on the randomness of the strings that are being generated. But every time I like ask the same question, I need the same answer, or I need close enough answer. And this is important for the PUF to work in these settings, for instance. Yeah, so did I answer your question? Good. Anything else? Yes.
So in some way, because is very similar to a chaotic system.
Is very similar to
A chaotic system.
a chaotic system? No, exactly. That was my point. It's not, because it needs to be deterministic in producing the outcome, right? So a chaotic system is very sensitive to the input, right? So if I change the input slightly, it can change the output a lot. But what you want here is that if I'm in a vicinity of some inputs, then my outputs are also in some vicinity. So that's the kind of properties that you want. But then the output scattered enough in the space that make this hard to know.
So I'm not very familiar at all with chaotic system, but I think somewhere in chaotic system there are some kind of island where if you have also phase diagram, where close points have almost the same output.
Close points are the same output.
And there are sometimes there are big islands, and sometimes there is very small islands.
Maybe in some regimes you would be able to use that, but as in full generality, like a random system is not a good PUF that we know, because it needs to have this like robustness property. Maybe, yeah, maybe that's a good point. I don't know, maybe that's like a good regime to have a look. Yeah, so there's like two properties that you need for a device that give me to be a PUF, apart from that like unpredictability, is that so you want this robustness thingy. So you want that every time and is like kind of close. And the second thing is that if I ask two very distant questions, I want to also see distant answer. So something that maps everything back to one point is very hard to maybe read, but that's useless, because I want to have several outcomes as well, and this is important. So yeah, if you combine these two properties, then like there's a restricted family of things, both classically and quantumly, that are interesting. So for instance, you cannot think of general quantum channel as good PUFs, because a lot of time, for instance, if you have a depolarizing channel, it will just like make the distances smaller and smaller. And this I don't want. I want like some distance to be preserved. So you can have some degree of, depolarization. If you're thinking of a PUF as a channel and not a unitary, you can have some degree of depolarization, but that will give you some compromise in the security. So you need to be careful of that. Yeah. Anything else? So okay, so I'll show you my last slide, which is now cryptography from. So you've seen cryptography from minimal assumption, from hardware assumption, and you can also do cryptography from learning. And so if you would have asked me, like, can you do cryptography from learning theory 2019, I would be, yes, that's like very cool. And so when you ask me now, I would say yes, but you need to be careful. Like, it's not trivial to construct cryptography based on hardness of learning assumption. The reason is that, and I will give just that in one sentence, and I know it will not make sense to you, but come and talk to me if you're interested. But The reason is that average case hardness and worst case hardness, they are very different and they have very different consequences. And sometimes things that are hard to learn on average, they have very weird properties that makes them not good for cryptography. If you're interested more, come and talk to me. I'll tell you more about this. But so just that this is not like, you know, I'm not the only person who has ever thought about that. And there's this like nice paper that came out last year. It's hardness of learning quantum circuit and its cryptographic application. And the idea is exactly give you also like alternatives way to do cryptography. And one of the things is that so there's this structure in quantum computation which is like very broad but very useful and interesting, and it's called random quantum circuit or random brickwork circuits. You know, it's been those terms being used. So it's a quantum circuit that you have this like 2 qubit gates that you apply them like 2 by 2, 2 by 2, 2 by 2, and then like you apply these between these two, and then like you just like follow this like brickwork structure. And so this is a very interesting circuit when I pick these 2 qubit gates to be random unitaries over the space of 2 qubits, right? Not over like the whole thing, like just over the space of 2 qubits. So when I do that, then the depth of this circuit tells you a lot of things. Like for instance, if I take these steps to be very long, asymptotically, this will give you exactly a random unitary, right? If I like take this to some depth, it will give you a T design. Less than some depth, it will give you something random, but like it's not very clear. So these are like the interesting regimes. So that. And so it's been shown that after a certain depth, which as you can imagine by this like hard thingy that I described, these circuits are hard to learn. And these are like really good building block to construct things out of it for some reason, because like one of the most important things is that these are even hard for quantum computers. So these are hard learning problems, no matter if you have classical or quantum devices. And yeah, so if you assume you have like a circuit like that, and you can make sure that you're running it after like certain depths, and you somehow use this inside your cryptography, then you can do cryptography with that. So this is one way of like doing cryptography based on hardware assumption. You can also think of like quantum physical unclonable function as another way that links this notion of learnability and you know, like cryptography from hardness of learning, because in fact, as of you know now that unclonability and learning are kind of like related. So this is also like another way of like having cryptography based on hardness of learning. And there's more. So this is something that's quite new. So like yeah, this paper was out 25. Yeah, very like recently people are doing that. But the idea itself is actually quite old. So if you've heard about LWE assumption or learning with error, which is in classical cryptography as one of our candidates for post-quantum, this is also somehow cryptography based on a hardness of learning assumption. But that, you know, that's a different story. But yeah, kind of like, yeah, you can think of things like that and construct your cryptography based on knowing or assuming something is hard to learn. And yeah, with that, I think I will finish. Any last questions, discussions? Yes.
Have you explored using cups for some classification? So any other class, for example, you presented in the last lecture?
So for the hybrid one, which are like the more practical stuff, I'm working on using it for coin flipping. We'll see which one come out. It's not so trivial because it's a bit. So one thing I tell you, like you remember I talked about this like trust assumptions, like being different, making things difficult. So for when you switch from authentication, which is a trustful setup, to things like coin flipping and bit commitment, which are mistrustful setup, things get really hard to work with a puff, because you know that eventually it can break. So you need to find like a setup that is not so trivial. But I think it can be done. So we're working on that. So if you're interested, I'm happy to have a chat. But I think you should be able to get some one-sided commitment or coin flipping out of this kind of like constructions. Classically, I think classically people have done bit commitment out of classical puff. But that's a bit of like cheating because the classical puff that they use in those papers, they're very good puffs. So they're almost like a one-way function. It's like almost identical to one-way function. So it's almost like they did it with one-way function, but it's just like, you know, the definitions are different. I don't, so one thing that they use puff a lot for in practice is for key generation and key storage. So there are some puffs that I was not very interested in them because they're kind of like boring in the setting we worked with, but there are some puffs that they produce only one response. So it's almost like this like key thingy. So like you push the bottom and it gives you like a random string. What's good about it is that it has that manufacturer trust assumption. So like you kind of like think of them as random number generators that are safe even against the manufacturer. So there are like applications like that. And in general, yeah, you can use that as use puff as some sort of key management system as well, because like you have this database and then you can like do some sort of key management with them. But these are all the things that I know. I think that you should be able to do a lot more with them, but it's kind of like a new field and it's niche. So, and I think it's only interesting when you bring it to the quantum setting, because in the classical ones, it's very good for like IoT security and this kind of like heuristic, low resource security. People use it a lot, but for like a little bit more hardcore cryptography, the classical regime is not so interesting, I think. Okay, let's go a little bit.
Let's have Mina again.
Thank you.